on astroparticle physics. And astroparticle physics, as we know, stands as a breathtaking intersection where the wonders of particle physics merge seamlessly with the celestial tapestry of astrophysics. It is an honor to have today with us somebody who would enlighten us on astrophysics and join us on this cosmic journey. May I take the pleasure to introduce Dr. Debanjan Bose. His work in the realms of high energy gamma astronomy, neutrino physics, and several other invaluable contributions to projects like icecubeneutrinoobservatory, magic, and hyper kamiokande resonates deeply with our exploration of the universe's most enigmatic mysteries. Dr. Bose has completed his BSc and MSc from University of Calcutta with a first-class degree and a Ph.D. in high energy physics from TIFR Mumbai. His research interests are primarily into astroparticle physics, high energy gamma astronomy, neutrino physics, and multi-messenger astronomy. He is currently working with icecubeneutrinoobservatory, the project which is recognized by CERN experiment, and is also working with MAGIC, major atmospheric gamma imaging Cherenkov telescopes, and various other projects. And he also working closely with HK Hyper Kamiokande, a neutrino observatory and experiment under construction. Sir, a very good evening and a warm welcome to this podcast.
Thank you very much for this nice introduction and for the invitation for this online presentation. So this gives me an opportunity to meet and interact with, I hope, many students.
Thank you, sir. Sir, actually, we already have got subscribers who have started asking questions. But before that, I would just like to ask you the first basic question: that if you can explain us what exactly is high energy astroparticle physics or high energy physics?
Okay, yeah. So I'll start. Before I start, I explain what is high energy or astroparticle physics. Let me tell you one incident. Just couple of days back, there is an article published in Science. It's about it says that they have detected there's a telescope in North America, Utah. So they have detected, they call it oh my god particle. It's a cosmic ray. I'll explain you what is a cosmic ray. So our Earth is continuously bombarded by some charged particles, charged nuclei. Most of them are protons and some higher nuclei. They're coming isotropically, means wherever we are on Earth, we get equal amount everywhere. However, they cannot penetrate the atmosphere, and that's why life survived because of that. So when they interact in the atmosphere, they produce secondary particles and photons. So we can detect those secondary particles and photons on ground, and indirectly we can detect that cosmic ray or the charged particles. So 2 days ago, this experiment called Telescope Array in USA, they have detected a cosmic ray that has energy 240 times 10 to the power 18 electron volt. So it's like the energy, if you read some of the articles, it's like energy like equivalent to if you drop a brick from a waist to on your foot, it's that much energy. Or if you hit a golf ball at almost 100 miles per hour, it acquires that much energy. The surprising thing is like for a brick or a uh, golf ball, you can imagine if falling very fast, if you're dropping a brick, that can carry that much energy. But a proton, which is so tiny, how a proton can get such high energy? So
Yes.
in astroparticle physics, that the main motivation is to identify from where these particles are coming. And once we know that, we also study how they are getting such high energy. This is the
Okay.
basic idea. That's the main idea,
Okay.
of course. But then these particles, what happens, since they're charged particles, when they travel through space, they're deflected by magnetic fields. So even if when we detect them on Earth, we cannot trace back their source. So we need some neutral messengers. And that's where gamma rays and neutrinos come into the picture because they are neutral, they are not deflected. So these cosmic rays may interact with matter at the source, some of them, and they can produce gamma rays and neutrinos. And if we detect them on Earth, we can identify the source. That's how this is all astroparticle physics, to study about cosmic rays and then neutrinos and gamma rays.
Okay. Sir, one question is that how is, I mean to say, how is normal physics, I mean to say, normal astrophysics and how high energy astrophysics, what is basically the difference? If you can just let us know.
Okay. So talk about astrophysics. Okay, astrophysics basically we are studying astrophysical objects like stars or supernova or galaxies. Now they emit all kind of radiations. We know that. I mean, the we know like still few decades ago, astronomy means we would only detect lights like visible light or maybe infrared. But later on, we realized there are sources. There are sources that also exit emit lights beyond the optical, the radio, ultraviolet, X-ray, gamma rays. So now these emission processes are different. I mean, the process by which optical light is emitted or radio is emitted, it's different when they emit gamma rays. So gamma rays and neutrinos, they are relativistic. They're moving relativistically. They have very high energies. So meaning, in order to produce such high energy particles, you need to stretch various physical processes to their limits. That need not be the case for optical or radio. I mean, there are cases when they can also emit relativistic particles, but not always that case. But when you're detecting gamma rays and neutrinos, you're always studying sources which are, I mean, where physics laws are stretched to their limits. Yeah? You're studying the relativistic universe, high energy particles. Okay. And just to give you an idea, like even on Earth, at currently the most energetic particle accelerator we have at CERN, they produce energy like 10 to the power 12. And when I started, I mentioned the cosmic ray detected is 10 to the power 18. Okay, million orders more energetic particles. So we do not know, like currently with whatever technology we have, we cannot accelerate particles to high energy. So we need to understand why they are produced and where they are produced. That's the main difference.
Sir, that means that when we are dealing with, I mean to say, high energy astrophysics, say for example, the area that you deal with, that means if I talk of the basic physics or the mathematical knowledge that I need versus astrophysics with high energy astrophysics, that means mathematically, do I need to know more about relativistic cosmology and relativistic astrophysics rather than the general astrophysics?
You're right. I mean, so if you look at very high energy emission processes, you need to know the relativistic processes. But it also helps when you know the other like normal like astrophysics, but we say not relativistic part. So basically, for us, we divide into two like thermal and the non-thermal. Thermal part is the part where they follow this black body radiations kind of thing. But non-thermal where processes involving like synchrotron radiations, inverse Compton scattering, then particle interactions, proton with photons, proton with another proton, this kind of thing. So we at high energy we deal with more of these processes, but often we need to know both sides.
Okay. Sir, we already got one question coming up from Shivam Kumar. He is telling that if you can, sir, please suggest a book on astrophysics.
That is difficult. Now there are so many books and so many articles available online. So if someone is starting for a very the beginner, the very starting, one can read that famous book by Frank Schuh. That one can try, but I know, I mean, many students ask me also, but I really don't know exactly. Like, there are so many books available. I mean, one has to see. There are very good books also.
We got another question, Samidha. Now, she is actually a very common. She is a very participative. She is telling that, sir, can I become a physicist after BTech?
Definitely. So currently in India, like, so I know there are many accomplished scientists who did BTech or BE, like engineering, and then they shifted to physics, and they have contributed exceptionally. I mean, there are many. So yes, definitely you can do that.
Okay, Sanket Thakur, sir, he is asking that we detect that much higher energy. So, what kind of process would happen in the early universe?
No, I mean the processes or the particles. I said this is not very early. So these are the things where happen afterwards. So like so normally you get high energy particles when a star dies. Supernova happens. When supernova happens, when they produce a shock. So in that shock, it has a very high magnetic field. Charged particles are trapped, and they get accelerated. They get energy. That's the one process.
Sir, one thing that keeps up, there's one another question coming up from cyber hashtag. Professor, what is the last or recent development in astroparticle physics? I think this is a very good question because I was also feeling to ask you, sir, if you can just.
Development in the sense, as I said, like this. So astroparticle physics, high energy physics. I said there are three messengers we have currently, like this cosmic rays, neutrinos, and gamma rays. Uh, so, uh, so cosmic rays, as I said, like we'd like to know from where they're coming. So, if you're interested, you can just search in the Google, like, oh my God, particle. It's only 2 days ago it was there. So you may learn about it. So, so the such high energy particles we are getting on Earth very rarely. Okay. So, in this case, when they try to trace back where it's coming, we don't have any idea exactly where they're coming from. So that's something people, physicists need to think about. I mean, they need to go back and look into what are the possible way they can explain. So I can clearly imagine for next few years there will be many papers appearing to explain this high energy cosmic ray. Then
Right.
earlier this year, the IceCube experiment, this Neutrino experiment, which is located at Antarctica, they have found evidence of high energy neutrinos coming from the center of our galaxy. So generally, if you galactic center has many sources and all kind of cosmic objects are there. They emit in all wavelength, radio to gamma rays. But this is the first time this year the neutrinos also being found. So with neutrinos, so neutrinos are always produced when some particles are involved in interaction, mostly proton. So proton interacting with matter. So neutrino detection proved that there are also particles or cosmic rays. So in this case, they said like these neutrinos are not coming from any particular source, but they're diffuse. Diffuse means there are cosmic rays, they're moving randomly in the galactic center, interacting with matter, the neutrinos are produced. So this is also a big result to get neutrinos from. Then there are neutrinos detected from a couple of other sources. And for gamma rays, I would say the last 20 years, they have produced wonderful results. So I have written some review articles. Maybe I can share the link later, and one can go through it to see what is the status of high energy gamma ray astronomy. Yes.
Sir, one thing also which was keeping me busy is that now in neutrino research also in this physics for students channel a few months back there was Dr. Jessica Turner from Durham University. She was also doing, she's still doing a research in neutrinos. Now the question is that why uh, physicists or scientists are so much I'm into taking up neutrino research, Because standard model tells that neutrino has got no mass, but we detect from experiment that neutrinos also got a mass. I mean to say, can you tell us that why neutrino research is very important?
Okay, so there are two aspects for neutrino. One is from astrophysics point of view, and other is from particle physics point of view. Okay, so in astrophysics, why we need to study neutrinos? Because as I said at the beginning, one of the main motivation in astroparticle physics is to identify cosmic ray sources, the energetic particles that we get. But because they're charged, when they travel, I said they're deflected. So they randomly move in the space before they arrive. So in order to identify the source, we need neutral messengers, so gamma rays and neutrinos. But what happens? Gamma ray production can happen by processes that does not involve cosmic ray. Okay, but neutrinos are only produced when a cosmic ray interacts at the source. So when we detect a neutrino from a source, then we can say with 100% certainty, yes, that is a cosmic ray, which we cannot say if we detect gamma ray. It may or may not be. That's the astrophysical part. But from particle physics, neutrinos, like as you said, like standard models say they don't have mass, but now we know they have masses because they oscillate, right? The oscillation is something which is beyond standard model already, a phenomena that has been established. Now, when we started measuring various other properties related to neutrinos, like how their mass eigenstates are mixed, which one is the which neutrino, like so there are flavor eigenstate that we detect, electron neutrino, muon or tau neutrino, and there are the mass eigenstates. So each flavor eigenstate is a mixture of mass eigenstates, three mass eigenstates. Now, which of these neutrino has the highest and which is has the lowest mass, this still not known. The mass hierarchy. So that has implications. Okay, in particle physics. Then, do neutrinos and antineutrinos oscillate same way or not? If oscillating, their oscillating behavior different, that gives an idea why our universe is matter dominated, not by antimatter. There are no antimatter. So various things that we can study or we can find the answers from neutrinos. So there are two things roughly.
So, sir, we have one question coming up. I would take all the one by one. Now, Sanket Thakkar is telling, sir, rest mass of proton is MeV. How can we get that much of ion energy by using Einstein mass energy equation?
I mean, is he saying how a proton gets high energy?
Yeah, that is also what I would ask Sanket if you can put it, because question is itself not a little bit clear.
Yeah. So
So,
how they get is it's you can imagine like a charged particle gains energy when it gets trapped in a magnetic field. Okay. So what happens like you might have studied like if there is a electron trapped in a magnetic field goes around, and as it goes around its gyro radius, Lama radius increases. Same happens here. If the source has very high energy magnetic field, charged particles are trapped, their Lama radius keeps increasing. They get energy like how the way cyclotron works, right? Or the synchron mechanism. So that's the process. That's so uh, for cosmic rays, the best uh, model which can explain the high this how protons are accelerated is called Fermi acceleration mechanism that Cornell has accepted. So in this, according to this model, so when the shocks are produced, like shocks means charged particles are moving very high speed, uh, and other the charged particles trapped in it, because the shock has a certain magnetic field, they move back and forth. They even attach to that shock and they move back and forth. And in this process, they gain energy. And at some point, when if they gain so much energy, they will escape. So then that magnetic field is not strong enough to hold them back. So that's how. That's the standard process how they get energy.
Sir, we got another question, and Sanket has already told yes that one. So thank you, sir, for explaining this. Cyber hashtag one has one question. He's asking, Professor, is there any way to experimentally detect virtual particles as we study them in quantum field theory?
I think this is beyond my.
Yeah, absolutely. I think
Sorry.
I mean to say astroparticle physics, that would be great. Right. Sir, what I would like to ask also to you is that this detect I mean to say you I was talking to you over the chat and you told me that yes, this is a very complicated and a difficult question. So I mean to say, if, not a difficult question to you, but it requires a lot of things to take into mind. But one thing is that, sir, the normal telescopes that we put in, say for example, one of my student already has got a telescope, small telescope, he has put it on and he keep on posting on my Facebook, etc. Moon and the craters, etc. I mean to say general part. Now, when we go to relativistic areas, high energy astroparticle physics, etc. What is the? I mean to say, I'm not asking sir that to explain the technology, but what is the difference in terms of the lens and first of all, what is the challenge if we use the normal astrophysics telescope? And what is the new technology and what are the things that have changed drastically from the general telescope? What are required to see those physically in the night sky? If you can, sir, please
Yeah,
explain us.
it's a very good question. I'd like to take it. Myself is an experimentalist. I do experiment. So telescope, when we talk about telescope, we always think as an optical telescope. A telescope as a definition is something that brings us information from far above some sources to us. And the telescopes are also different for different detection techniques. Like, so optical telescope, you have a mirror and then this lens, you take images or whatever. But at high energy, when we detect a neutrino or a cosmic ray or a gamma ray, then the techniques are very different. They're telescope, all right, but they're very different. For example, for a cosmic ray detections, if we want to detect them on Earth, then what we need, because we detect the secondary particles of photons produced by this cosmic ray in the atmosphere. So on ground, we are detecting charged particles of the photons. Okay, even though there are photons, but the arrangements are different from an optical telescope. And charged particles, you need something, some. It can be a solid state detector. It can be even some water in a container. So these charged particles, what happens? They move at a very high speed, almost relativistically. In fact, they overtake the speed of light in the medium. So light speed reduced when you travel through a medium because of the refractive index. But the charged particles, they travel with the speed more than the speed of light in the medium. That happens, they produce a radiation called Cherenkov radiation in a medium, either in water or even in atmosphere. So one can detect these Cherenkov radiations on ground, and you can detect indirectly. So if you if you start reading, or if you think telescope means it's like optical telescope as a lens and all, no, it's just different. The processes are different, the techniques are different, and similar techniques are also used for gamma ray as well as neutrino. Okay, so telescope, the technique itself is quite different. I mean, I'm not explaining. I mean, if you want me to be, it's difficult to, maybe with some pictures it would have been easier to explain. But maybe I would suggest the students, like, you can try. I name you three experiments. One is Pierre Observatory. That's the largest area they have, 3,000 square kilometer. It's located in Argentina. You may go visit their site and you can see how it works. Other is this icecubeneutrino experiment, which is in Antarctica. It's in buried in ice. It's 1 cubic kilometer volume. And third is, as I worked on this Magic Gamma telescope. So you can visit their websites, and they have, you can find that you look at the pictures, and they have nicely explained in brief how this telescope works.
Sir, we have one question from Physics Salt. He is asking, hello sir, I have a question like, as the astroparticle physics deals with high energy particles, how it helps the string theory for experimental validation?
Again, I think this is difficult to answer.
I think that in terms of string theory, string theory validation is extremely, I think in one way it is very theoretical. And this is a totally experimental physics. So I think
Maybe I
that,
can
yeah.
make one comment. So I started with the highest cosmic ray detector, which has come up, published a couple of days back. So one of the theories, like maybe they are produced by some cosmic trains. Okay, but I can comment beyond that. I mean, my knowledge about string theory is almost nil. So
So physics salt is asking, Pierre Auger Observatory is also active in cosmic rays.
their primary task is to detect cosmic rays. That's their primary goal.
So that means that technologically, these telescopes from the normal astroparticle physics to high energy astroparticle physics, there is a technological shift in terms of detecting those astroparticle physics.
Not techno. I'll say the techniques are different. So when you say like when you so we detect optical, you need something. When you are going to detect X-ray, you cannot use the same telescope. So optical has certain like wavelength and frequency, energy. X-rays have different. So you cannot use the same technique for both, right? Similarly, when you're going for particle detection, they need different arrangements.
So in India, where and how can we do have observatories observing these high energy radiations and astroparticle physics?
Okay, yeah. So India, there is one experiment which is located in Uti. In fact, I would say India has a legacy of doing cosmic ray experiments uh, since independence. Like you all know the Vava Atomic Research Center BRC in Mumbai. So Homi Vava is one of the pioneers. Like he had worked with. He's one of the stalwarts of cosmic ray physics. So when he started this in India, came back. So initial thrust was to do cosmic ray research because in olden days, before the particle accelerators were built, cosmic rays, I mean, people did particle physics through cosmic ray detection. So India has a long history. So they even built an underground detector in the Kolar Gold mines in Karnataka. Now that is no longer operational. So for cosmic detection, right now there is an experiment run by TIFR at UT, but they detect cosmic rays not at that high energies, because when you go to very high energies, these particles are extremely rare. I mean, maybe you will be detecting one such particle in maybe few years. Okay, so so you need very big detectors. But the one I just talked about, the experiment name is Grapes in UT. So they detect cosmic ray at little more energy, around 10 to the power 15, 10 to the power 16 electron volt. So they have these cosmic ray detectors. Then at Ladakh, recently BRC has built one big gamma ray telescope, and TIFR already has a setup there in Ladakh. So they do gamma ray astronomy. And for neutrino, there was a plan to build an Indian neutrino observatory, but that for some reason so far not materialized. Hopefully, something will come up soon.
That means, sir, we need mostly these type of things would happen on a high elevation mountain where the sky is clear.
No, the elevation needed for something else. Because if we are detecting the secondary particles, okay, so whenever the cosmic ray or gamma ray comes into the atmosphere, they interact at an altitude of say at a height of around almost 20 kilometers in the atmosphere. and the secondary particles will, a shower will produce, okay, cascade. Now, this at some after certain point, this secondary particles will lose energy. They will be absorbed. Okay. So in order to catch them, you need to go higher up. So if higher up means you can, because they may not survive unless if the cosmic ray doesn't have very high energy, they may not survive till the sea level. So it's better you go at higher altitude to detect them. That's for cosmic ray and gamma ray if you're detecting them on ground. But for neutrinos, it's other way. Neutrinos, they don't, they have, they're very shy particles. They hardly interact. Okay, I mean, most of them pass through Earth without interaction. Like I give you an example. Like Sun is producing almost 10 to the power, I don't know, maybe 10, 11 neutrinos per second per centimeter square, like through our thumb per second, even now passing through. Most of them simply passes through without interactions. Okay, once in a while, one will interact. So for them, you need to build detectors either in some tunnels. Tunnel to go inside the tunnel, there is other factor like you need to reduce the background or surrounding backgrounds are also reduced. But also you need some because the way they detect, you also need some large volume of water or ice, some transparent medium. I mean, there are other methods also, but many experiments they use water and ice. Okay, so that's how this ice cube experiment works. I mean, it's maybe I'm not able to explain it properly, but as I said, like to have better idea, you can one can visit those websites.
Sir, we have two, three questions. I think these are relevant. First is that, is there a violation of Lorentz invariance in the cosmic rays like 10 electron volt?
No, I mean, okay. So if there are violations, so we try to measure this Lorentz invariance violation, but in a slightly different way. We use this uh, cosmic rays or neutrinos or gamma rays, assuming there is a source that producing say high energy gamma rays or neutrinos. Now, according to this theories, like because of this small fluctuations or whatever in space time. Now, suppose the source is emitting both an high energy neutrino and a low energy neutrino, or both high energy gamma ray or low energy gamma ray. Now, and assuming they are emitted at the same time, but because of this fluctuation in space time, they will arrive at different time with certain delay. From this delay, one tries to give a estimate about this LIV, whether actually it's valid or. So far, we have only produced upper limits. That's the only thing we can say about this Lorentz invariance violation.
One more question coming up. This is, I think, it's a pretty general question. What is the difference among cosmology, astronomy, and astrophysics?
That's good. So cosmology deals with how universe created, it expanded, with inflation, all these things. Astronomy, in the past, people used to only do astronomy. Like you observe a source in the sky, you make a catalog, its position, etc. Now, astrophysics is you also see what kind of physical processes are responsible for emission of light or emission of particles. You study the physics about that source. That's the astrophysics.
So one more question coming up. Uh, Professor, annihilation and pair production of particles is done on same energy scale. How can you explain this?
Mm, mm, well, at the moment, difficult to answer this and how to put it. Yeah, maybe I'll skip this. Sorry, difficult to explain at this point.
Do we find any rigorous source of cosmic rays? and how to explain the discrepancy in the flux graph with the distance.
I'll answer the first, but I didn't understand the second question. What does it mean? Discrepancy in the flash graph means? Maybe I first answer this. The source. No, we have not. Okay, we have found a cosmic ray source, a couple of cosmic ray sources. For example, so as I said, like to identify the cosmic ray source, we need to detect gamma rays and neutrinos. Though we have detected many gamma ray sources, but it's difficult to claim that they are cosmic ray source also, because gamma rays can also be produced by processes that does not involve cosmic ray. But we have detected neutrinos from couple of sources, both uh, received by IceCube. Both are extragalactic, but not within our galaxies. There are galaxies beyond our own galaxy. So we have detected neutrinos from those sources. So neutrino means definitely those sources are accelerating cosmic rays, because that's how neutrinos are produced. And apart from that, uh, there are some evidence that there are also supernovae in our galaxy that are producing cosmic rays, because the gamma ray signature that we have from those supernova can be explained only if they are produced from neutral pion decay. The neutral pions are produced only when cosmic rays interact. So yes, we have some evidence about cosmic ray sources, but we need some more data and more sources that needs to be.
Actually, he is asking flux density graph of the cosmic rays, like the observed flux is more than the calculated flux from here.
I don't think so. Is there any plot? So the cosmic ray plot, what you generally see if you type in Google cosmic ray spectrum, you'll see a power law spectrum, falling curve with increasing energy. So in cosmic ray, it's actually uh, discovery happened first, and later people tried to explain the spectrum and then develop theory. Okay.
Sir, cyber hashtag is asking, Professor, is there any particle known in the universe which interacts with the dark matter of dark energy?
Definitely with dark matter. So all the experiments that I'm associated with are currently working with cosmic ray. So there are also various theories like often this gamma rays or neutrino might interact with some dark matter and they will create some uh, standard model particles, or dark matter they can annihilate with other dark matter various theories, and they will produce standard model particles like neutrinos or gamma rays along with others. So there are theories, and these experiments keep looking for dark matter signatures regularly. But so far,
Sir, my question is now a little bit broad. Now, the thing is that I just want to know a little bit from you the process. I mean to say, for example, there is an observatory, we have a telescope. Now, there is a burst, whatever, in terms of high energy physics of particle. Now, if you can tell all of us, because this would be a first hand knowledge, because you are into this field for many years, if you can, I mean to say, let us not go into technical details, but overall the entire process physically, I mean to say, gamma ray burst happens, the telescope detects, and it comes to computer, the scientists evaluate, what do they see, is it a graph or a colorful area, from there what kind of numerical figure. So if you can give us an overall idea right from the burst till the coming to the computer, what you people actually do. If you can please let us know.
okay. So how it works? So I'll explain with the gamma ray telescope. That should be easier because the gamma ray burst. For example, you mentioned gamma ray burst. So, so gamma ray burst happens. Okay. Now, and it's producing gamma rays, and it's detected. So, if you're detecting using gamma ray telescopes on Earth, we what we get is okay. I'll not go to that very technical. So there's a telescope. the gamma ray, they detected some gamma ray. So we get some electric pulses. Okay, so there are detectors which called photomultiplier tube. It produces an electric pulse. Okay, so this gamma ray telescope, they have certain camera made of many of such photomultiplier tubes. Okay, so this gamma ray interacts in the atmosphere and produces a shower, and that shower will produce an image in this camera. So each pixel or photomultiplier tube, it has a certain electric pulse. We collect this electric pulse. We try to first we determine from where it's coming, from where the gamma ray has come, because we need to identify the gamma ray burst source position. Then what is the energy of the gamma ray? That's also important. And there may be many. Are they all have same energy? Normally it's not same energy. They will have certain spectrum. Spectrum means you have many gamma rays of different energies. Okay. So this spectral shape, so we first identify the source where it is in the sky, and then from the spectral shape, we try to explain what kind of mechanism, physical mechanism, can actually explain this gamma ray spectrum. Okay, so this is how. So then try to explain why that gamma ray burst has produced, what the likely mechanism that producing this gamma ray. And of
So,
course,
sir,
in between, there are various other processes like how we clean and how to identify the signal from background. I'm not going into that, but this is the roughly thing.
so it basically then comes to the computer, and then you take the data, and then you start a research.
Yes, everything now, everything is computerized. Everything. You collect the data in certain format, okay, and store, and then you do the analysis offline, sometimes online, depending on your priority.
Okay. Sir, my next question would be, rather, I won't say question. Now, all these images, say for example, that we see in the telescope, say for example, very famous Horsehead Nebula, or the that what is called the Eye of the God, different, for example, black holes, or elliptical galaxy, etc. Now, what I am willing to know, sir, is that when there is a telescope, say for example in an observatory which is mounted, whatever the electric impulse etc is getting, do they actually, I understand what you're talking of cleansing, because I was talking to one of the
Yeah,
astronomer,
I
Kevin
understand.
Perry.
Maybe I'll explain. Okay, I understand what you're trying to say. Like you said, this various crab nebula and how exactly do the image is produced.
I mean to say, are they actually captured by that, or
No, no,
it is
no, that's
later
kind of.
rendered?
So suppose you have your every telescope has certain field of view. Okay, means like you are observing a certain area of the sky and your source is located, or you are trying to map a source. Now, the emissions are not coming uniformly everywhere. If it is uniform, you'll see a flat image. But all these structures you see, like that means different amount of photons are coming from different region of the source or the sky. That's what you make a presentation with different colors. So it looks attractive, but that's the idea is. You getting different amount of photons or particles from a source or the region in the sky, you try to map. Then if you go back, okay, I have detected one photon from here, two photons, there's a two photons will have red, one photon will have orange. You'll go on adding, you'll at the end you'll get a nice picture.
That means the elliptical galaxy, spiral galaxy, whatever we see, it is after rendition, it does not come exactly like that.
No, after I mean how it will, I mean they are very far. How you're going to from Earth, they're simply point source. But sometimes you see the extension because some are extended, or then you see the image.
I got it. Thank you very much, sir. Sir, if you can just let us know on what is this Hyper Kamiokande, the research that you are doing on.
So Hyper Kamiokande is okay. So this is a third generation of experiment. So there is in Japan there is a mine called Kamioka. So these experiments are located in that mine. So they are called Kamiokande. Kamiokande then stands for other things, neutrino detection, etc. So initially it was built, the first one, the Kamiokande experiment was built in the 70s, 80s. Their initial motto was to target the proton decay, the grand unification theory that says the proton will. But then in 1987, a supernova happened. And when if a star has very high mass, not our sun, which is not that massive, if there are massive star when it dies, it there is a core collapse. It at certain point it cannot sustain its gravity anymore. Okay? It sustains gravity through fusion, right? Radiations. When it starts producing iron, it cannot sustain its gravity anymore. It starts to collapse. That's when supernova happens. And during that collapse, it produces huge amount of neutrino. I mean, most of the energy during core collapse are carried by neutrinos, huge amount. In fact, optical lights uh, escape much later because it's so dense. So in 1987, this Kamiokande experiment detected some of the neutrinos. There were few other neutrino experiments at that time. So they realized the detector can be used for neutrino detection. They also started using detecting the solar neutrinos. Sun also produces, as I said earlier, huge amount of neutrinos through these fusion reactions. So with this success, then they realized they need to build even bigger detector because these neutrinos, as I said, they have very small interaction crossing. They are very shy. They hardly interact. Only way to capture them if you have huge volume. So they build Super Kamiokande. That is still running. So they detect neutrinos from sun, then even neutrinos produced in the atmosphere by cosmic rays, etc. And they have produced some wonderful results. And both Kamiokande and Super Kamiokande received Nobel Prizes. Okay, both. Now they are planning, they have some physics goals. Now they realize that they need to build even bigger detector, more sensitive. So that's why Hyper Kamiokande now under construction to study neutrinos. Neutrinos, it will do both. As I said earlier, neutrino has both aspects. One is the particle physics part and the astrophysics. So they'll do both.
Sir, I got a very relevant question from Sheikh Shamshad Pasha. Sir, guide us on pursuing high energy physics as career in India.
Yeah, good question. So high energy physics, right now I would say there are two main branches. One is the particle physics branch. Okay, so India is part of the Sun experiment, LHC and others, and there is a big community for doing particle physics, both experiments, theory, phenomenology. So there is like TIFR is one place, Science Institute one place. Now there are various IITs, ISES. They all many of them in this institute which are part of this high energy physics community. And for astroparticle physics, the high energy astrophysics, there are not many options currently. So TIFR is one place, maybe BRC, and now there are some people in some IITs or universities, but I would say next 4 5 years there will be many more astroparticle physicists in India, and there is this neutrino physics that falls in between the particle physics and astroparticle physics because it covers both. Neutrino physics is also India has a very big community. So there are many universities, many scientists were part of foreign collaborations, or they
So,
also
what is
try.
the educational qualification, if you can? What
No, in MSc, do any MSc or this, regular MSc or even some specialized will do. But then, if you want to study high energy physics, I would say like if you want to do Ph.D. theory, that's something. Of course, then you do physics and then go for. But if you want to do some experiment or phenomenological study, phenomenology means you have the data and try to explain it through models. Then I would say good to have some software knowledge because nowadays all calculations, etc. Even for doing theory, it's important. There are various, like if you want to solve certain equations, etc., better if you can learn certain software. It will be really useful. So, and if someone is interested, then one can also go for some, I don't know, a summer school, or right, go for a project for a couple of months to have an overview. So it gives you a better idea.
From cyber hashtag. Professor, according to our current observatories, up to what distance we can detect any particle from it? A big event like supernova, gamma ray burst is happening somewhere. I mean, so he wants to know possibly up to what distance we can detect the particle which is coming from the
For
source.
neutrino, it can come from very, very far. No issue. But for gamma rays, there are limits because this gamma rays, as if you're interested in high energy gamma rays, the gamma rays often tend to interact with low energy photons which are there in space. And if they interact with low energy photons, they will produce electron positron pair and the gamma ray will be lost. So you cannot detect gamma rays from very far. The gamma ray universe is somewhat limited. But for neutrino, there is as such no restrictions. And cosmic rays, they can come from far, but then, as I said, we don't know where they're coming because they're deflected so many times. So it's difficult to know from where they're coming or from how far.
So we are coming to almost to the end of our today podcast. You have answered almost all the questions. So my curiosity is that what exactly is your research area and what exactly you are currently researching into?
Okay, so when I started with high energy gamma ray astrophysics, so so I we had an experiment which was located in Pachmari. So it's no longer there. So similar array was built in Ladakh. It's still working. So gamma ray experiment is one such I did, and after that I moved to neutrino, icecubeneutrino. Initially, I was doing neutrino astrophysics, then neutrino properties. So currently, my research involves multi-measure. Like if we, so we can study as to understand a source, astrophysical source. We need to gather information, all kind of possible. Like if it is emitting optical, radio, then we need to collect all the data and try to model it. Why? Because if you're only doing gamma rays, like there was a story like some blind people were looking into elephants and they're trying to see what it is. So unless you collect all the information, you won't get the actual picture. So it's called multi-messenger study. You collect all data from wherever, which telescope possible, and you try to build a model which is very much realistic. That's one thing I do. And there are also certain applications we are trying out, like all these cosmic ray particles and all. There are ways to do certain applications. We can. There are muons produced when these cosmic ray interact. These muons can be used to map, say, volcanoes or some structures, ancient structures. So this kind of things one can do.
So one question last, if you don't mind, can we take it? Professor, when a supernova or high energy gamma ray burst happens, then particle emitted with it will move with constant velocity or deaccelerates first and then attain constant velocity. Can we detect?
Yeah. So whatever, like when supernova or the gamma ray to few distance, all these things happen because of the high density of matter. And after a certain distance, these particles, the photons almost become free streaming. So whatever happens there, it may have an impact, but on Earth or with detectors in space, I mean, there will be some changes we'll see, but definitely we can detect. And sometimes with those impact, we can uh, determine certain properties of those sources. But yes, we can detect.
So lastly, what I would like to ask you, why are these sources located at very extreme cold places like Arctic, Ladakh, and almost near the why it is not in a very
So what
hot
it
place
is
like the desert?
so techniques that we use to detect gamma rays, eventually we don't detect the gamma ray directly. We detect the secondary photons, but those photons are optical. Okay, so you need a very dark environment, and since we use the atmosphere as a medium, we can operate in the night, clear moonless night, no cloud, no moon. So of course you need to go to a very remote place,
Why
and
don't we use desert? Why are we using only
no,
the
no,
very
desert also
cold places?
you can use, you can use. So in so there are experiments which are now under constructions. They will come up in there is a experiment in Namibian desert called case gamma ray experiment. One is coming up, and then this cosmic ray experiment I mentioned is also kind of a desert. And few days back, as I said, the highest cosmic detected in Utah. It's also kind of desert. You need to go to remote places. So it depends on like the, see when you go to a very remote place or like South Pole, you also need resources, right? So you have to keep in mind. It's not that I suddenly one morning I get up and go to South Pole and build an experiment. Like you have to think about logistics and etc. But those are the best places to do it without any interference, no human activities, etc. So you can work peacefully.
Sir, one last question, cyber hashtag. I don't know how to pronounce this. Please throw some light on Bremsstrahlung.
The breakdown is a process when a charged particle comes near the nucleus, it gets bent and it's produced radiation. That's the Bremsstrahlung process. So gamma rays can also be produced in this process. It's a process of production of say gamma ray.
Sir, any last message for the young people, young astrophysicists who are willing to make
So
up their career? Anything
what
you
I
would
can
suggest?
say, like what I can say, I mean, this is the, I mean, next 10 years, there are many experiments are coming up, whether it's in astroparticle physics or in say optical, radio, or even gravitational detectors. So next 10 years are really very exciting. Maybe I think we are going to see many new results, many discoveries, unexpected things. So I think it's the right time to join astrophysics community as a whole, not just astroparticle. Astrophysics as a whole, it's going to be very exciting.
There are a lot of scopes. There are a lot of ways in which students can study, and this is a very promising area. Okay, last question. I think cyber hashtag would be typing it out. We will just take one question. Samidha is asking, sir, now in present situation, what is the main motto of physics?
Motto of physics, I mean, of course, to explain everything that's happening around us, explain everything.
I mean,
It's,
theory of everything or a
yeah,
grand unified theory.
like everything, like, yes, that's in one liner. Like,
Sir, from your studies that you did from BSc, MSc, and TIFR in Mumbai, in PhD, etc., was there any event, a person, or anything that motivated you to go into high energy physics rather than theoretical physics or anything else?
okay, no, so when I joined TIFR, like, okay, so maybe like many others, I had a curiosity about astrophysics. Okay, I read some of the books by Stephen Hawking and all. I was curious, but then I went there. Then I had chance of knowing of other experiments, other fields. I always wanted to do something related to astrophysics, and this. But then there were other options also to join, say, radio or optical. But then I chose this arranged astrophysics because it was not that time. It was not that conventional. Something a little more challenging. I felt, and yeah, I mean, all this. So, and another thing I realized, like, I will get an opportunity to work on every aspect, like an experiment, theory, simulation, everything to learn. I mean, that's a good exposure I had. Other things, if already telescope is the technique is established, you simply take the data and do physics. But what kind of like efforts are gone into building such experiments? Okay, I think it's also good to learn and be part of that.
Absolutely. So this is the last question of today. Professor, how this high energy physics will lead us to unification of theories, that is theory of everything?
But I mean, I'm not an expert. What can I say? Like we need to go at higher and higher energy. Like for example, string to the higher dimension and all. So how do I say? Maybe even for example, I said like this Kamiokande experiment. One of their main physics goal is to study this proton decay. So according to this theory of unification, protons are also not a stable particle, right? So if they find any indication that protons decay, that might help understand this or unification of all these forces. That's what I can say.
So before I end, a quick announcement to those who are watching today. We are actually have been enlightened and learned a lot of things from Dr. Debanjan Bose. He has been talking for almost 1 hour on astroparticle physics, high energy physics. On the 3rd of December, on the same channel, Dr. Sudeshna Ganguly, particle accelerator and scientist at Fermilab, would be joining us to talk more about particle physics. Now, you see, Sir has told about astroparticle physics, and Sir has already explained the real, essence of particle physics. On the next episode, that is next Sunday, we will be encountering particle physics from Dr. Sudeshna Ganguly, and I think with Dr. Debanjan Bose's knowledge on astroparticle physics and particle physics, we can get a better knowledge. So this is a note of thanks coming up. Very much thank you, Professor. Thanks to you, sir. And thank you very much
Thank
for
you.
coming. And this has been a real wonderful session. We learned a lot of things from you. This is the first time I'm going to say, so Samidda is telling that, sir, I am also from West Bengal. So a lot of young boys, girls, etc., they are coming up. So again, a note of thanks to you, sir. Thank you, Professor.
Thank you.
So
Thank you
wish
very
you
much.
all the best for your career. And thank you, sir, for spending 1 hour and more to enlighten us. And I mean to say, heartfelt thanks to you. Thank you very much, sir.
Thank you. Thank you very much. I also enjoyed.
Thank you,
Thank
sir. Thank you.